Have you ever wondered how big websites like Facebook and Twitter handle massive data and traffic without crashing? Well, one of the things that can help with handling big amounts of traffic and data is the concept called eventual consistency. Now let's imagine we have a social media app that we've built and we only have one database. And at the beginning this is working great because we don't have a big amount of traffic yet. And usually one of the goals of big websites is to serve their customers or users very fast. But when our app goes global and we have users all over the world, it can be challenging serving all of those users very fast from one database. And in today's digital world, applications often rely on distributed systems, where the data is spread across multiple servers or nodes. Let's draw this out. I have here a very simple diagram that shows that we have the user, one client, the server, and database. I'm not really gonna go into the architecture of the app, I'm just gonna focus on the database. Here we have only one database, and every time the user updates, selects or inserts any data, it's gonna go into this database. And this can work great because we don't really have to care about the complexity of distributed system or multiple nodes. But when we have a requirement to serve multiple users very fast, then we might think about read replicas or some other distributed system in order to serve our users fast. Now when we have multiple servers or nodes, this is where things get complicated. Because now, how would we serve a user if we have multiple databases where we keep the data? For example, like this. Now it depends how the architecture of your app is done. This might mean that you have different databases for different microservices, which would eventually mean having different data in each database. But here we're only talking about one monolithic service or one microservice specifically, where we need to replicate the data across multiple databases in order to serve our user fast. In AWS, we have read replicas, which is basically replicating your database but optimizing for reading data, which will have a very fast read time but not very fast write time. And usually if you are getting the data, you're gonna use one of those read replicas, or if you're writing the data, you can write it in one database only. And then we're faced with complexities and challenges of how we're going to keep that data consistent across the multiple nodes or the multiple read replicas. Eventual consistency is a consistency model used in distributed system or particularly NoSQL databases. It prioritizes high availability and consistency by allowing temporary inconsistencies across multiple nodes. And usually the way it works is any service we use, for example AWS, they're going to provide and manage this service for us most of the time. All of the nodes and databases will be grouped into one, where the server is going to communicate with those, and then the data will be replicated across the different nodes. Usually AWS or any other service we're going to use, they can manage most of that for us. They can give us one IP address where we're going to communicate with and to get and write data, like a load balancer or whatever it might be, but we are not managing the replication of data and where we're getting the data from. That's one way to do it. And there's also other ways where we can actually handle all of that ourselves. So we can have multiple databases, manage them all, make sure that the data is replicated and it's in all the correct places, and make sure we're reading and writing data from the correct nodes. Now, if you imagine that we're using AWS to manage everything for us, we're going to have one database system, which is going to have multiple database nodes inside. And these nodes are all going to communicate with each other to make sure that the data is replicated across themselves. So the way that eventual consistency would work in a big system is if one of the users try to update some data, for example, the profile picture on a social media app, the request at the beginning will only update one of the nodes, which would mean that one of the nodes now have the new profile picture, and the system will try to replicate the data asynchronously to the rest of the nodes. But in the meantime, if we get a request that goes to another node from a different user to get the profile picture, they might see the old data. So I'm gonna mark these as yellow, which are they still don't have the new data yet, and the system will try asynchronously to get the data. But if another user tries to access the data from this node, they will see the old profile picture, but eventually all of the data will be propagated to all of the nodes and the data will be consistent. Hence the name eventual consistency. Now, you might be wondering why choose eventual consistency over a strict consistency model. If you have a website with a lot of traffic, The eventual consistency has a few benefits. For example, it allows for high availability. If you have multiple database nodes, if one of them fails, the website can still operate because you still have data across the other nodes. And if the data is just replicated, then you still serve all of the users. Maybe a bit slower, but you can still serve most of the users. And then we have low latency. Whenever some of the users updates anything, the request will only update one node and then return with a response. Whereas if you have strict consistency, you have to wait for all of the nodes to be updated before you return. And third, we have scalability, which means that eventual consistency simplifies the scalability of your databases. It allows for adding new nodes easily without caring how the data is propagated or when it's being propagated, because the system should already handle all of that. And eventual consistency addresses the challenges of data consistency in large-scale distributed system while ensuring high availability and performance. And it allows applications to remain responsive and provide good user experience even when dealing with network issues, high traffic, or server failures. Now, of course, when building anything, there's some trade-offs that you need to think of for eventual consistency. The main trade-off is not having consistent data all of the time. There's going to be temporary windows where you're not going to have consistent data, but if you don't require a strict consistency, then this model might work for you. And while that window of temporary inconsistent data is very short usually, it might not be suitable if you have, for example, a financial app where all the data needs to be consistent all of the time. And in those cases, strict consistency might be a better choice, but it also comes with potentially a reduced availability and performance. And in my opinion, eventual consistency is a very powerful tool that allows many high traffic websites to operate and give good user experience. And while it might not be suitable for you and your website, I think it's very good to understand the concept and what it provides so you can make better decisions when you're designing your next application. So if you have a distributed system, make sure you think about eventual consistency and to try and see if it's gonna work for you. I have changed this video a little bit. I've changed the lighting and I'm using OBS now. You're also gonna see my mic in the videos now. I know I was hiding before, but this gives better audio quality, so I'm gonna keep it in. I'm using OBS, and I don't think I've set it up for the highest quality, but I'm still trying to figure it out. So if you have any feedback for that, put it down in the comments below. And also if you have any feedback for the video or the ideas I'm talking about, also put it down in the comments below. But yeah, that's been it for this video. Thank you very much for watching. Enjoy the rest of the day. Happy coding. Bye.